Hi, my name is John Smith, and today I'll be going over Team 7's Pluto Exploration Mission. Team 7's members include Trevin Kim, Rosalind Ontiveros, Tori Rofe, Chase Visser, and myself. Today we'll be covering a mission overview, introduction and background information, modeling and important assumptions, calculations and analysis, and a summary. Multiple Pluto rendezvous missions were designed using both chemical and nuclear electric propulsion to perform a scientific study of Pluto. For each design, mission requirements state a maximum prime mission completion time of 20 years, with a launch window from Earth between 2029 and 2035. The spacecraft C3 must be below 150 kilometers squared per second squared for a 2,500 kilogram dry weight of the spacecraft, and must not fall below an altitude of 100 kilometers in its science orbit. Our chemical propulsion transfer mission starts with a single impulse burn from a low Earth orbit of 200 kilometers to Jupiter with a delta V of 6.71 kilometers per second on June 7, 2034. It takes a trailing side flyby of Jupiter to increase the spacecraft's heliocentric velocity by 1.4913 kilometers per second, with a single impulsive burn into an elliptical science orbit around Pluto on the 22nd of September, 2042. The selected low-thrust mission follows a similar mission with a Jupiter flyby and single impulsive burn to capture at Pluto on the 7th of September, 2044. As you can see, the requirements for C3 and time of flight are met for both trajectories. Planetary bodies, such as Pluto, past Neptune, are referred to as trans-Neptunian objects, or TNOs for short. They are believed to have originated from the Kuiper Belt. For most trajectories to TNO objects, gravitational assist flybys are used, and most commonly occur around Jupiter due to its large mass and Pluto's extremely distant orbit with an inclination of 17 degrees. There are many potential studies that could be performed in a science orbit around Pluto, making it a very useful planet for scientific study. Scientists believe there may be a water-based ocean under the solid nitrogen glaciers of Sputnik Planitia. Pluto's nitrogen sublimation cycle also poses an interesting source of study. An elliptical orbit around Pluto could study the believed cryovolcanic activity on Pluto, or analyze one of the dwarf planet's 5 moons. The lack of small craters on Pluto have led researchers to believe that its surface composition could hold the key to understanding the formation of the Kuiper Belt itself, or the comets that originate from it. It may also unveil secrets about the formation of our entire solar system. For this mission, NASA's SLS Block 2 launch vehicle was used, with a maximum launch C3 of 150 kilometers squared per second squared. For the chemical propulsion trajectories, a Super Draco propulsion system was used, with a vacuum ISP of 300 seconds, making it more effective than any other chemical propulsion system on the market. For the nuclear electric trajectories, Aerojet Rocketdyne's NEP Next C engine was used, with an ISP of 4,220 seconds, making it extremely efficient. To simplify the trajectory calculation process, several important assumptions were made. We assumed there would be no hardware malfunction and used a two-body patched conics approach for solving the mission trajectories. We also assumed that the plane change to account for Pluto's inclination would occur at the flyby of Jupiter. In our calculations, all objects are assumed to be perfectly spherical point masses. Only one mass is acting on the spacecraft at any given time, and that our mission would start with a 200-kilometer low Earth orbit. The constants used for hand calculations are displayed here. NASA's Ames trajectory browser was utilized to find an ideal trajectory at Jupiter for the impulsive mission design. For our low-thrust missions, JPL's Malto program rendered this trajectory for a spiral-in mission design, this for an impulsive design, and this to include an additional flyby to study the Kuiper Belt object, Eris. Many opportunities for flybys to Jupiter were available between the launch window of 2029 and 2035. This led us to use the windows available from Jupiter to Pluto instead to determine possible launch dates and work backwards from there. The following 2 slides provide a brief overview of important equations utilized to calculate all required elements of chemical propulsion trajectory by means of the two-body problem, including planetary flyby and rendezvous, planetary capture orbits, and the Lambert problem. This was achieved through the utilization of outside resources and analysis methods, such as MATLAB, NASA's Ames Trajectory Browser, NASA Horizon's Ephemeris data, V-infinity matching around Jupiter, and viable launch windows from generated pork chop plots. To optimize these trajectories, we prioritized a low fuel burn while maintaining a total mission time of less than 20 years. We also traded a higher launch C3 for a lower overall total mission delta V. Multiple trajectories were calculated and considered for the chemical propulsion mission, with mass propellant burned being the most important variable considered. From this, we selected our final chemical propulsion trajectory, leaving Earth on June 7, 2034, and arriving to Pluto on September 22, 2042. This trajectory had the smallest amount of fuel burned and the shortest time of flight to Pluto, making it the optimal trajectory for the mission. This same process was done for our nuclear propulsion trajectories, with our massive propellant burn once again being the most important factor to the down selection process. From this, we selected the impulsive end trajectory due to its lower fuel cost. An analysis of our final selected chemical propulsion trajectory is summarized in the tables shown, including important metrics and trade-offs utilized in our selection process. The selected flyby of Pluto includes a small impulse burn to match the correct departure delta V from our calculations and pork chop plots. At Pluto, the team selected a highly elliptical orbit with an eccentricity of 0.7 in order to save fuel when arriving at the dwarf planet. Here we have a final summary of the chemical propulsion trajectory. Some notable facts about this trajectory are the gain in heliocentric velocity around Jupiter, which we found to be 1.4913 kilometers per second squared. Kilometers per second. At Pluto, the delta V was found to be a very low 0.4623 kilometers per second, due to our spacecraft traveling relatively close to the heliocentric velocity of Pluto at arrival. In total, this mission took 8.29 years to complete, with a final delta V of 8.664 kilometers per second and a propellant mass of 44,970 kilograms. For the low-thrust mission, we selected the trajectory with an impulse in maneuver for a free capture at Pluto on the 30th of July, 2024. The total time of this mission was 15.59 years, with an extremely low propellant mass of approximately 1,200 kilograms. The single-impulse, low-thrust mission, with an additional study of the Kuiper Belt object Eris, was eventually not selected due to additional fuel costs and additional flight time. Finally, we have our compliance matrix. This highlights each of the mission requirements and the validation methods we used to ensure that each mission requirement was met. As you can see, all of the presented mission requirements were successfully met for this project.